Subscribe to the channel so you don't miss out on any of these videos. Imagine a universe where the very building blocks of existence, every atom, every molecule, every speck of matter, are caught in an endless cycle, a cosmic dance that has been ongoing for billions of years. Picture this: the stars that light up our skies, the planets we walk on, and even the atoms in our own bodies are all part of this grand, intergalactic recycling program. How does the universe manage this? How does it take what was once part of a distant star and turn it into something entirely new? This isn't just science fiction, it's a mystery woven into the fabric of the cosmos itself. And at the heart of this mystery lies the cosmic baryon cycle, a process so fundamental, yet so elusive, that understanding it might unlock the secrets of how everything we know came to be. But what exactly is this cosmic cycle? How does matter flow between stars, galaxies, and the vast spaces between them? And why is this process so crucial to the evolution of the universe? By the end of this deep dive, you'll not only know what the cosmic baryon cycle is but also why it might hold the answers to some of the biggest questions about the cosmos. To start unraveling this, let's break down the term itself. Baryons are a category of subatomic particles that include protons and neutrons, the core components of atoms. Essentially, baryonic matter is the stuff we can see and touch: stars, planets, gas clouds, and yes, even us. What makes the cosmic baryon cycle fascinating is how this matter doesn't stay static. Instead, it moves, transforms, and gets recycled in a process that spans the entire universe. Think of it as the ultimate recycling program, but on a scale that's almost impossible to comprehend. Now, let's zoom out for a moment. The story of the cosmic baryon cycle starts with one undeniable fact: the universe is in constant motion. Matter flows between stars, drifts into the vast expanses of intergalactic space, and then somehow makes its way back into galaxies to form new stars, planets, and everything else. This flow of matter isn't random. It's driven by processes like stellar explosions, gravitational forces, and even the mysterious pull of dark matter. One of the most dramatic parts of this cycle occurs when stars die. Massive stars, for example, end their lives in spectacular explosions called supernovae. When this happens, they eject enormous amounts of gas and heavier elements into space. This material, which was forged in the star's core over millions of years, doesn't just vanish. Instead, it becomes part of the interstellar medium, a vast, diffuse mixture of gas and dust that fills the space within galaxies. But that's not the end of the story. Over time, this interstellar material can cool and clump together under the influence of gravity, eventually forming new stars. Some of this material might also end up in the swirling disks that form planets, moons, and other celestial bodies. In other words, the atoms that once made up an ancient star might someday become part of a planet, or even a living organism. What's truly mind-boggling is how this process isn't limited to individual stars or even single galaxies. Matter also flows between galaxies, moving through the vast, near-empty spaces of the intergalactic medium. Scientists have observed streams of gas being pulled out of galaxies by gravitational interactions, as well as massive flows of material falling into galaxies from cosmic filaments. These exchanges of matter are a critical part of how galaxies grow and evolve over time. One of the most exciting tools scientists use to study the cosmic baryon cycle is spectroscopy. By analyzing the light coming from distant stars and galaxies, astronomers can determine what elements are present in a given region of space. This has allowed them to trace the movement of baryonic matter across vast distances and uncover patterns in how it's recycled. For example, researchers have found that galaxies like our Milky Way are constantly pulling in fresh gas from the intergalactic medium while simultaneously ejecting material through processes like supernovae and powerful winds driven by black holes. This constant push and pull creates a dynamic equilibrium that sustains star formation and shapes the structure of galaxies. But here's where things get even more intriguing. We don't actually know where all the baryonic matter in the universe is. Observations suggest that a significant portion of it exists in a diffuse, hard-to-detect state in the intergalactic medium. This is sometimes referred to as the missing baryon problem. and solving it could provide crucial insights into how the cosmic baryon cycle operates on the largest scales. Another key player in this cycle is feedback, processes that regulate the flow of matter in and out of galaxies. For instance, when a supermassive black hole at the center of a galaxy accretes matter, it can release enormous amounts of energy in the form of jets or winds. These outflows can push gas out of the galaxy, slowing down or even halting star formation. At the same time, gravity and cooling processes can pull fresh gas back into the galaxy, restarting the cycle. The cosmic baryon cycle is also deeply connected to the larger-scale structure of the universe. Galaxies are not isolated systems. They exist within a vast cosmic web of dark matter and gas that stretches across the universe. This web provides the scaffolding for the flow of baryonic matter, guiding it along filaments and into the dense regions where galaxies form. To truly grasp the scale and importance of this cycle, consider this. The same processes that recycle matter in the universe are responsible for creating the elements essential for life. The carbon in your DNA, the oxygen you breathe, and the iron in your blood were all forged in the cores of stars and then distributed through the cosmos by the very mechanisms we've been discussing. The cosmic baryon cycle is a reminder of how interconnected everything in the universe is. It shows us that nothing is truly lost, matter is simply transformed, reused, and reshaped in an ongoing cosmic symphony. As scientists continue to study this process, they're not only learning more about the history of the universe but also uncovering clues about its future. From the birth of the first stars to the formation of galaxies like our own, the cosmic baryon cycle has played a pivotal role in shaping the cosmos. Yet there's still so much we don't understand. What drives the flow of matter between galaxies? How does this cycle change over billions of years? And what can it tell us about the ultimate fate of the universe? These questions keep astronomers looking up, searching for answers in the endless expanse of space. The quest to understand the cosmic baryon cycle isn't just about satisfying human curiosity. It's a window into the fundamental processes that govern the universe. To fully appreciate its significance, it's crucial to dive deeper into the mechanisms that keep this cycle running. At the heart of it all are the forces and phenomena that drive the movement, transformation, and recycling of matter. Let's explore the first major mechanism, galactic winds. These aren't the gentle breezes you'd feel on Earth. They are powerful streams of gas driven by intense energy. Galactic winds often originate from processes like supernova explosions or the energetic activity around supermassive black holes. When a massive star dies in a supernova, the explosion not only scatters heavy elements, but also generates shockwaves that propel surrounding gas into space. Similarly, when a black hole accretes matter, it can release immense energy in the form of jets and outflows, creating winds that blast gas out of a galaxy. These galactic winds are a double-edged sword. On one hand, they prevent galaxies from holding on to all their gas, which might seem counterproductive for star formation. But on the other hand, they enrich the intergalactic medium with heavy elements, setting the stage for future cycles of star and galaxy formation. Without these outflows, the universe would lack the diversity of elements needed to create planets and life as we know it. Then there's the phenomenon of accretion. While galaxies lose matter through winds and outflows, they also gain fresh gas from their surroundings. This gas often comes from the vast cosmic web, a network of filaments composed of dark matter, gas, and galaxies that stretches across the universe. As gravity pulls gas along these filaments, it funnels into galaxies, replenishing their reserves and fueling new star formation. This balance between ejection and accretion is a critical part of the cosmic baryon cycle. It's a dynamic system where galaxies act as both sources and sinks of baryonic matter. If a galaxy loses too much gas without gaining any in return, its star formation slows down or stops altogether. Conversely, if a galaxy pulls in too much gas, it can trigger bursts of star formation that dramatically alter its structure and appearance. Now, let's zoom out even further and consider how this cycle operates on the largest scales. The intergalactic medium, IGM, the vast expanse of gas that exists between galaxies, is a key player in this process. The IGM isn't empty. It contains a significant fraction of the universe's baryonic matter. Most of this gas is in a hot, diffuse state, making it difficult to detect directly. However, its presence can be inferred through its interactions with light, such as the absorption features it creates in the spectra of distant quasars. One of the most intriguing aspects of the IgM is how it acts as both a reservoir and a highway for baryonic matter. Gas flows out of galaxies into the IgM through processes like galactic winds and tidal stripping, but it doesn't stay there forever. Over time, this gas can cool, condense, and fall back into galaxies, continuing the cycle. The role of temperature in this process cannot be overstated. Gas in the IgM is often heated to millions of degrees by the energy released during events like supernovae and black hole activity. At these temperatures, the gas becomes highly ionized, meaning its atoms lose electrons and form a plasma. This hot, ionized gas can remain in the IgM for billions of years before cooling enough to be pulled back into galaxies. What makes the cosmic baryon cycle even more fascinating is how it's influenced by the mysterious substance known as dark matter. While dark matter doesn't interact directly with baryonic matter, its gravitational influence shapes the large-scale structure of the universe. Dark matter forms the scaffolding around which galaxies and gas clouds gather, guiding the flow of baryonic matter along cosmic filaments. Without dark matter, the cosmic baryon cycle as we know it might not exist. Observations of the cosmic baryon cycle have also revealed a surprising trend. The rate at which matter is recycled varies depending on the size and type of galaxy. In massive galaxies, the strong gravitational pull can retain gas even after powerful outflows, leading to slower recycling rates. In smaller galaxies, however, outflows can be so effective that they expel most of the gas into the IgM, making it harder for these galaxies to sustain star formation over long periods. This variability has profound implications for the evolution of galaxies. For example, it helps explain why some galaxies appear quenched or no longer forming stars, while others remain active. Understanding these differences is a key goal of modern astrophysics, as it sheds light on the diverse ways galaxies grow and evolve. But the cosmic baryon cycle isn't just a story about galaxies and gas, it's also a story about time. The universe is constantly changing, and the processes that drive the cosmic baryon cycle have evolved alongside it. In the early universe, when galaxies were smaller and more gas-rich, the cycle was likely more rapid and chaotic. Today, with larger, more mature galaxies and a less dense IgM, the cycle operates on longer timescales. By studying the cosmic baryon cycle, astronomers are piecing together a timeline of how the universe has changed over billions of years. This includes understanding the role of large-scale phenomena like galaxy clusters and superclusters, which are regions of the cosmic web where matter is especially concentrated. These massive structures act as hubs for the flow of baryonic matter, influencing the cycle on scales that dwarf individual galaxies. And yet, for all we've learned, many questions remain. For instance, how do different types of feedback, like those from supernovae versus black holes, affect the cycle in different environments? What role does magnetic fields play in shaping the flow of gas? And how does the cosmic baryon cycle intersect with other cosmic processes, like the formation of cosmic rays or the behavior of dark energy? As technology improves, astronomers are developing new ways to study these questions. Advanced telescopes like the James Webb Space Telescope and future observatories will allow scientists to observe the cosmic baryon cycle in unprecedented detail, capturing the movement of gas and the formation of stars across a wide range of cosmic environments. The more we learn, the clearer it becomes that the cosmic baryon cycle isn't just a background process. It's a driving force behind the universe's evolution. It connects the smallest particles to the largest structures, linking the past, present, and future in a continuous cycle of transformation. As we continue unraveling the mysteries of the cosmic baryon cycle, it becomes evident how interconnected every aspect of the universe truly is. This process doesn't merely influence stars and galaxies, it dictates the composition of the universe itself. From the smallest atom to the grandest galaxy cluster, everything participates in this intricate cosmic dance. One of the most profound aspects of the cosmic baryon cycle is its role in creating the elements essential for life. In the earliest moments after the Big Bang, the universe was dominated by hydrogen and helium, with trace amounts of lithium. These light elements formed the foundation, but they were insufficient for the complex chemistry required for life. It was through the cosmic baryon cycle, specifically the birth and death of stars, that heavier elements, like carbon, oxygen, and iron, were forged and distributed across the cosmos. Stars act as the factories of element production. During their lifetimes, stars fuse lighter elements into heavier ones through nuclear fusion. In smaller stars like the Sun, this process primarily produces helium from hydrogen. In more massive stars, the fusion extends to elements like carbon, oxygen, and even iron. However, once a star exhausts its fuel, its death triggers events like supernova explosions or the formation of neutron stars, spreading these heavier elements far and wide. This distribution ensures that the materials necessary for life and planet formation are available in the interstellar medium, ready to be recycled into the next generation of stars and planets. The cosmic baryon cycle's ability to enrich the universe with heavier elements highlights its fundamental importance. Without this process, planets like Earth, and by extension, life as we know it, would not exist. Every atom in our bodies, from the carbon in our cells to the iron in our blood, was forged in the heart of a star and later scattered across space through the cosmic baryon cycle. Another fascinating aspect of this cycle is how it shapes the appearance and behavior of galaxies. Galaxies are not static entities. They evolve and change over time due to the inflow and outflow of matter. The interaction between a galaxy and its surroundings often determines its fate. For example, galaxies in dense clusters are more likely to lose gas through processes like ram pressure stripping, where the pressure of the hot intracluster medium removes gas from a galaxy as it moves through the cluster. This loss of gas can quench star formation, transforming a once-active galaxy into a dormant one. Conversely, galaxies in less dense environments might experience a steady inflow of gas from the cosmic web, sustaining star formation for billions of years. This diversity in environments creates the incredible variety of galaxies we observe today, from spiral galaxies like the Milky Way to elliptical and irregular galaxies. The cosmic baryon cycle also explains one of the most perplexing observations in modern astrophysics: the missing baryon problem. Observations of the early universe indicate that baryonic matter, ordinary matter made of protons, neutrons, and electrons, accounts for about 5% of the universe's total energy density. However, when astronomers attempted to account for this matter in the local universe, they found that a significant portion appeared to be missing. The solution to this mystery lies in the diffuse gas of the intergalactic medium. Advances in observational techniques, such as the detection of the warm-hot intergalactic medium, WIM, through its absorption of X-rays and ultraviolet light, have revealed that these elusive baryons are hiding in the vast spaces between galaxies. This discovery not only resolved the missing baryon problem but also underscored the importance of the cosmic baryon cycle in maintaining the balance of matter across the universe. Now, let's turn our attention to the role of feedback in regulating the cosmic baryon cycle. Feedback mechanisms, particularly those driven by supermassive black holes and supernovae, act as cosmic regulators, preventing galaxies from hoarding all their gas and stifling the cycle. When a supermassive black hole becomes active, it can release vast amounts of energy in the form of jets and radiation. This energy heats the surrounding gas, preventing it from cooling and condensing into stars. This feedback not only shapes the evolution of the host galaxy but also influences its surroundings, creating large-scale structures like galactic bubbles and cavities in the intergalactic medium. Supernova feedback, on the other hand, is a more localized process. When a massive star explodes, it releases a shockwave that drives gas out of the galaxy. This ejected gas can later cool and fall back into the galaxy, continuing the cycle. The interplay between these two types of feedback ensures that galaxies maintain a delicate balance, neither running out of gas too quickly nor accumulating too much at once. The cosmic baryon cycle is not limited to individual galaxies. It operates on cosmic scales, shaping the evolution of the universe itself. One of the most striking examples of this large-scale influence is the formation of galaxy clusters. These massive structures, containing hundreds or even thousands of galaxies, are the result of billions of years of gravitational interactions and the flow of baryonic matter along the cosmic web. The gas within these clusters, known as the intracluster medium, is heated to extreme temperatures, emitting X-rays that allow astronomers to study its properties. This hot gas plays a crucial role in the cosmic baryon cycle, acting as both a reservoir and a conduit for matter. Despite our growing understanding of the cosmic baryon cycle, many questions remain unanswered. For instance, how do magnetic fields influence the movement of gas within galaxies and the intergalactic medium? What role do cosmic rays play in heating and ionizing gas? And how does the cycle interact with dark energy, the mysterious force driving the accelerated expansion of the universe? To answer these questions, scientists are turning to advanced simulations and cutting-edge observational tools. Simulations like the Illustrious and Eagle projects model the evolution of the universe from its earliest moments to the present day, providing insights into the dynamics of the cosmic baryon cycle. Observatories like the James Webb Space Telescope and the Square Kilometre Array promise to revolutionize our understanding by detecting faint signals from distant galaxies and the intergalactic medium. The cosmic baryon cycle is more than just a scientific concept. It's a testament to the interconnectedness of the universe. It shows us that nothing in the cosmos exists in isolation. Every star, galaxy, and particle of gas is part of a larger, dynamic system. By studying this cycle, we not only uncover the processes that shape the universe but also gain a deeper appreciation for our place within it. The cosmic baryon cycle is also deeply intertwined with the story of the universe's evolution, stretching back to the formation of the first stars and galaxies. In the early universe, about 400 million years after the Big Bang, the first stars began to light up the cosmos in an era known as cosmic reionization. These first-generation stars, known as population 3 stars, were composed almost entirely of hydrogen and helium, as heavier elements had yet to be formed. Their immense heat and luminosity caused the surrounding hydrogen gas to become ionized, breaking it into its constituent protons and electrons. This era was crucial for jump-starting the cosmic baryon cycle. When these early stars ended their lives in massive supernova explosions, they seeded the surrounding space with the first heavy elements. These elements were then incorporated into the next generation of stars and galaxies, introducing a level of complexity to the cosmic baryon cycle that had never existed before. As galaxies began to form and grow, the interplay between gas inflows and outflows became a defining characteristic. Early galaxies had abundant access to pristine gas from the cosmic web, which flowed in long filaments, fueling rapid star formation. However, the intense energy output from newly formed stars and active galactic nuclei often pushed gas out of these galaxies, creating a feedback loop that regulated their growth. This balance was essential for preventing galaxies from growing too quickly or collapsing under their own weight. One of the most fascinating aspects of this process is the scale at which it operates. The cosmic baryon cycle is not just a phenomenon confined to individual galaxies or clusters. It spans the entire observable universe. The cosmic web, a vast network of filaments composed of dark matter and gas, serves as the framework for the movement of baryonic matter. Gas flows along these filaments into galaxies, where it can form stars, and is later expelled back into the intergalactic medium, enriching it with heavy elements. These interactions reveal how the cosmic baryon cycle acts as a cosmic recycler, ensuring that matter is constantly reused and repurposed. Without this recycling process, the universe would have exhausted its supply of star-forming gas billions of years ago, leading to a much darker and less dynamic cosmos. Instead, the interplay between inflows and outflows has allowed the universe to remain vibrant and active for over 13 billion years. The role of cosmic feedback in this cycle cannot be overstated. Supernovae, as mentioned earlier, are critical drivers of this feedback. When a massive star explodes, it releases an enormous amount of energy, creating shockwaves that can push gas out of a galaxy. This gas doesn't disappear, however. Instead, it enters the intergalactic medium, where it can cool and eventually fall back into galaxies, restarting the cycle. This process ensures that galaxies are not isolated systems, but are constantly exchanging matter with their surroundings. Active galactic nuclei, AGN, also play a significant role in regulating the cosmic baryon cycle. These are regions at the centers of galaxies where supermassive black holes are actively accreting matter. As matter falls into the black hole, it releases immense amounts of energy in the form of radiation and powerful jets. This energy can heat the surrounding gas to such high temperatures that it becomes difficult for the gas to cool and condense into stars. By doing so, AGN feedback helps to moderate the rate of star formation, preventing galaxies from growing too rapidly. The cosmic baryon cycle is also deeply connected to the large-scale structure of the universe. Observations of galaxy clusters, the largest gravitationally bound structures in the universe, have revealed how the cycle operates on these immense scales. The intracluster medium, a hot, X-ray emitting gas that fills the space between galaxies in a cluster, contains a significant fraction of the cluster's baryonic matter. This gas is thought to have been ejected from galaxies through processes like supernova feedback and ram pressure stripping. Over time, it contributes to the enrichment of the intergalactic medium, ensuring that heavy elements are distributed across the cosmos. Interestingly, the cosmic baryon cycle also provides insights into the mysterious nature of dark matter. While dark matter itself does not participate in the baryon cycle, its gravitational influence is crucial for shaping the cosmic web and guiding the flow of baryonic matter. Without the scaffolding provided by dark matter, the cosmic baryon cycle would not be able to operate on the scales we observe today. This interplay between visible and invisible matter highlights the complexity and interconnectedness of the universe. Modern telescopes and simulations have allowed scientists to study the cosmic baryon cycle in unprecedented detail. Instruments like the James Webb Space Telescope and the Atacama Large Millimeter/Submillimeter Array, ALMA, are capable of observing the inflow and outflow of gas in distant galaxies, providing direct evidence of the cycle in action. Meanwhile, simulations like the Illustris and Eagle projects use supercomputers to model the evolution of the universe, capturing the intricate dynamics of the cosmic baryon cycle across billions of years. These advancements have also shed light on some of the unresolved mysteries of the cosmic baryon cycle. For instance, while we now understand that the warm-hot intergalactic medium, WIM, contains a significant fraction of the universe's baryons, many details about its composition and distribution remain unclear. Observing the WIM directly is challenging because its diffuse nature makes it difficult to detect. However, recent observations of X-ray absorption lines have provided tantalizing glimpses of this elusive component of the universe. Another area of active research is the role of magnetic fields in the cosmic baryon cycle. Magnetic fields are known to exist throughout the universe, from the interiors of galaxies to the vast expanses of the intergalactic medium. These fields can influence the movement of gas, shaping the dynamics of the cycle in ways that are not yet fully understood. Future observations and simulations will be essential for unraveling these complexities. Ultimately, the cosmic baryon cycle is a testament to the resilience and adaptability of the universe. It shows us how matter, energy, and gravity work together to create a dynamic and ever-changing cosmos. From the birth of the first stars to the formation of galaxy clusters, the cosmic baryon cycle has played a central role in shaping the universe as we know it. By studying this cycle, we not only gain a deeper understanding of the cosmos but also uncover the profound connections that link every part of the universe to every other. The story of the cosmic baryon cycle is far from complete. As new technologies and discoveries push the boundaries of our knowledge, we will continue to uncover the intricacies of this universal process. Each revelation brings us closer to answering the fundamental questions of existence. Where did we come from? How did the universe evolve? And what does the future hold for the cosmos and everything within it? This journey into understanding the cosmic baryon cycle also prompts us to consider its role in the eventual fate of the universe. While the cycle has sustained star formation and galactic evolution for billions of years, it is not an infinite process. The gradual depletion of cold gas within galaxies and the heating of the intergalactic medium over time point to a future where the cosmic baryon cycle will slow down, and the universe will enter a quieter, less active phase. This idea ties into the broader concept of the universe's heat death. As stars exhaust their fuel and fewer new stars form due to the diminishing availability of cold gas, galaxies will slowly fade into darkness. The cosmic baryon cycle, which has long acted as the engine of galactic growth and renewal, will eventually sputter to a halt. However, the matter itself will not disappear. It will continue to exist in different forms, scattered throughout the universe, waiting to tell the story of its origins. Interestingly, this eventual decline in activity offers a new perspective on the role of the cosmic baryon cycle. While it has been a driver of cosmic vitality, it also serves as a reminder of the transient nature of energy and matter. The cycle ensures that nothing goes to waste, that every atom of hydrogen or heavier element finds a purpose in the cosmic dance. Yet, it also highlights that every beginning has an end, and every end leaves behind the building blocks for a new beginning. The philosophical implications of the cosmic baryon cycle are as profound as its scientific significance. It mirrors the cycles we observe in life and nature, from the water cycle on Earth to the life cycles of living organisms. In many ways, it is a cosmic reflection of the principle that energy cannot be created or destroyed, only transformed. This cyclical view of the universe invites us to think about our place within this vast, interconnected web of matter and energy. As we study the cosmic baryon cycle, we also uncover the delicate balance that governs the universe. For instance, the interplay between star formation, supernova feedback, and gas inflows is finely tuned. Too much star formation would quickly deplete the available gas, halting the cycle prematurely. Conversely, too little star formation would leave galaxies unable to grow and evolve. This equilibrium suggests a universe that, while chaotic and dynamic, operates within certain constraints that allow for long-term sustainability. One of the most fascinating questions about the cosmic baryon cycle is whether it operates in a similar way in all galaxies or if each galaxy has its own unique version of the cycle. Observations have revealed that different types of galaxies experience the cycle in vastly different ways. For example, massive elliptical galaxies, which are often found in the dense environments of galaxy clusters, tend to have low rates of star formation and are dominated by hot, X-ray emitting gas. In contrast, spiral galaxies like the Milky Way are rich in cold gas and have ongoing star formation, making their cycles more active and dynamic. Dwarf galaxies, on the other hand, present a particularly intriguing case. These small galaxies are highly sensitive to feedback processes, and their shallow gravitational wells make it easier for gas to escape into the intergalactic medium. As a result, the cosmic baryon cycle in dwarf galaxies is often less efficient, leading to lower rates of star formation. However, this inefficiency can also make dwarf galaxies excellent laboratories for studying the early stages of the cycle and the processes that regulate it. Beyond individual galaxies, the cosmic baryon cycle also plays a crucial role in the evolution of galaxy clusters and the large-scale structure of the universe. In galaxy clusters, the intracluster medium serves as a reservoir of gas that has been stripped from galaxies through processes like tidal interactions and ram pressure stripping. This gas is often heated to millions of degrees, making it difficult to cool and condense into stars. However, over billions of years, some of this gas may cool and fall back into galaxies, contributing to the cycle on a cluster-wide scale. The cosmic baryon cycle also interacts with the mysterious force known as dark energy. Dark energy, which is driving the accelerated expansion of the universe, affects the dynamics of the cycle by influencing the distribution of matter on large scales. As the universe expands, the density of the intergalactic medium decreases, making it harder for gas to flow back into galaxies. This interplay between dark energy and the cosmic baryon cycle raises questions about how the cycle will evolve in the distant future, and whether it will continue to sustain the universe's activity. On smaller scales, the study of the cosmic baryon cycle has practical implications for understanding the formation of planetary systems and, ultimately, the origins of life. The heavy elements produced by stars and distributed through the cycle are the building blocks of planets and living organisms. Without the cosmic baryon cycle, the universe would lack the diversity of elements needed to create rocky planets, water, and organic molecules. In this sense, the cycle is not just a mechanism for recycling matter, It is a process that creates the conditions for complexity and life. Recent advancements in technology have opened new windows into the cosmic baryon cycle. Instruments like the James Webb Space Telescope and the Extremely Large Telescope are providing unprecedented views of distant galaxies, allowing scientists to observe the cycle in action across cosmic time. These observations are complemented by state-of-the-art simulations that model the behavior of baryonic matter under different conditions, offering insights into the processes that drive the cycle. As we look to the future, the study of the cosmic baryon cycle promises to yield even more profound discoveries. By unraveling the mysteries of this cycle, we gain a deeper understanding of the forces that shape the universe and our place within it. The cosmic baryon cycle is not just a story of stars and galaxies. It is a story of transformation, balance, and interconnectedness that touches every aspect of existence. The cosmic baryon cycle reminds us that we are all made of stardust. The atoms in our bodies were forged in the hearts of stars and distributed across the cosmos through the very processes we seek to understand. As we study the cycle, we are also studying ourselves, our origins, and our ultimate connection to the universe. It is a story that transcends science, inviting us to reflect on the nature of existence and the incredible journey that has brought us to this moment. The journey of understanding the cosmic baryon cycle doesn't just reveal the mechanics of galaxies and matter, it invites us to confront some of the most fundamental questions about the cosmos. As the cycle propels the universe forward, shaping galaxies and star systems, it hints at the interconnected fabric of existence, where every piece of matter plays a role in the larger cosmic story. This is not merely an astronomical phenomenon, it is a universal narrative of creation, destruction, and rebirth. One of the most captivating aspects of the cosmic baryon cycle is its universality. No matter where in the cosmos you look, the cycle persists. From the smallest dwarf galaxies to the largest clusters, the processes of inflow, outflow, and recycling occur on a grand scale. This uniformity raises a compelling question. Is this cycle a feature unique to our universe, or could it be a fundamental property of matter itself, applicable even beyond our observable cosmos? The role of the cosmic baryon cycle in the early universe adds another layer of intrigue. During the first billion years after the Big Bang, the universe underwent a period of rapid star formation known as the cosmic noon. During this time, galaxies were forming stars at rates far exceeding what we observe today. The cosmic baryon cycle played a central role in sustaining this star formation by efficiently cycling gas into galaxies and enabling the creation of new stars. However, as the universe expanded and aged, the efficiency of the cycle began to decrease. The reasons behind this shift are still an area of active research. Cosmic noon also gave rise to the large-scale structures we see in the universe today. Galaxies formed along vast filaments of dark matter, and the cosmic baryon cycle acted as the engine driving their growth. The interaction between baryonic matter and dark matter during this period is particularly fascinating. While dark matter provided the gravitational scaffolding for galaxy formation, baryonic matter filled these structures, cycling through stars and intergalactic space. The relationship between these two components, one visible, one invisible, shaped the evolution of the universe in ways we are only beginning to understand. As the universe continued to evolve, feedback processes became increasingly important in regulating the cosmic baryon cycle. In massive galaxies and clusters, the presence of active galactic nuclei, AGN, added another layer of complexity. Powered by supermassive black holes at their centers, AGN release immense amounts of energy, heating the surrounding gas and preventing it from cooling. This feedback process creates a delicate balance. While AGN activity can suppress star formation, it can also help sustain the cycle by redistributing gas within galaxies. The cosmic baryon cycle is also closely tied to the phenomenon of cosmic starbursts. These intense periods of star formation occur when large amounts of gas are funneled into galaxies, often due to mergers or interactions with neighboring systems. Starbursts provide a unique window into the dynamics of the cycle, as they involve rapid inflows of gas, heightened star formation, and powerful feedback processes. Observing these events allows scientists to study the cycle in overdrive, revealing insights into how galaxies grow and evolve under extreme conditions. On the other end of the spectrum, the quenching of star formation in galaxies offers clues about the eventual fate of the cosmic baryon cycle. In quenched galaxies, star formation has effectively stopped, and the cycle has slowed to a crawl. These galaxies are often surrounded by hot gas halos that prevent new gas from cooling and accreting onto the galaxy. Understanding why and how galaxies quench is a major focus of modern astrophysics, as it sheds light on the ultimate limits of the cycle. Quenching also has implications for the broader ecosystem of the universe. When galaxies stop forming stars, they cease to enrich the intergalactic medium with heavy elements. Over time, this could lead to a less diverse chemical composition in the universe, affecting the formation of new stars, planets, and potentially even life. The cosmic baryon cycle, therefore, is not just a mechanism of matter recycling, it is a determinant of cosmic diversity and complexity. One particularly intriguing mystery related to the cosmic baryon cycle is the apparent missing baryon problem. Observations suggest that only a fraction of the universe's baryonic matter is accounted for in stars, galaxies, and hot gas. The rest, known as the missing baryons, is believed to reside in diffuse, low-density regions of the intergalactic medium, particularly in structures called the warm-hot intergalactic medium, WIM. The cosmic baryon cycle likely plays a role in distributing matter into these elusive regions, but their exact properties remain poorly understood. Efforts to detect the missing baryons are ongoing, with missions like the upcoming Athena X-ray Observatory expected to shed light on this enigma. Advancing our understanding of the cosmic baryon cycle requires a combination of observational and theoretical approaches. High-resolution simulations like Illustris and Eagle have been instrumental in modeling the cycle across cosmic time. These simulations incorporate the complex physics of gas dynamics, star formation, and feedback processes, allowing scientists to test different scenarios and compare them with observations. Meanwhile, telescopes like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Square Kilometer Array, SK, are providing detailed observations of gas in and around galaxies, revealing the intricacies of the cycle in unprecedented detail. The insights gained from these studies are not just academic, they have practical implications for our understanding of the universe's history and future. By mapping the cosmic baryon cycle across different epochs and environments, scientists can reconstruct the timeline of galaxy evolution, from the first stars to the modern universe. This, in turn, helps refine our models of cosmic evolution and provides a framework for interpreting observations of distant galaxies and quasars. As we delve deeper into the cosmic baryon cycle, we are reminded of the interconnectedness of the cosmos. Every atom of matter, every photon of energy, and every particle of dark matter is part of a grand, interwoven tapestry. The cycle is a testament to the universe's ability to recycle and repurpose its resources, ensuring that nothing is wasted and everything contributes to the larger narrative. The beauty of the cosmic baryon cycle lies not just in its scientific intricacy but in its philosophical resonance. It speaks to the cyclical nature of existence, where every end is a new beginning, and every piece of matter has a role to play in the eternal dance of creation and destruction. As we continue to explore this remarkable process, we are not just learning about the universe, we are learning about ourselves, our origins, and our place in the infinite expanse of space and time. The philosophical implications of the cosmic baryon cycle invite us to reflect deeply on the nature of existence. Matter that was once part of distant stars, long extinguished, may now exist in the air we breathe or the cells of our bodies. The universe is not merely a vast expanse of emptiness, it is a dynamic, living system where every particle has traveled across unimaginable distances and epochs, carrying with it the history of countless cosmic events. Understanding this cycle connects us to the cosmos in a profound way, reminding us that we are not separate from the universe but are intrinsic parts of its ongoing story. Exploring the role of the cosmic baryon cycle also challenges our understanding of entropy and order in the universe. On one hand, the cycle exemplifies the constant push towards equilibrium and the dissipation of energy, hallmarks of the second law of thermodynamics. Yet, within this inevitable march toward disorder, The cycle also fosters complexity, giving rise to stars, planets, and even life. It demonstrates that even within a framework governed by entropy, localized pockets of order and creativity can emerge, sustained by the intricate flow of matter and energy. One of the most striking features of the cosmic baryon cycle is the diversity of its manifestations across the cosmos. In spiral galaxies like the Milky Way, the cycle operates through a relatively steady balance of inflows and outflows, supporting sustained star formation over billions of years. In contrast, elliptical galaxies, often the result of mergers, exhibit a more chaotic and turbulent version of the cycle, with intense bursts of star formation followed by long periods of quiescence. Studying these differences helps astronomers piece together the evolutionary histories of galaxies and understand how their unique characteristics are shaped by the cycle. In dwarf galaxies, the cosmic baryon cycle takes on an entirely different character. These small, low-mass galaxies are highly susceptible to the effects of feedback, where even a modest amount of star formation can drive powerful outflows that expel gas into the intergalactic medium. This sensitivity makes dwarf galaxies valuable laboratories for studying the cycle's limits. They also hold clues about the early universe, as their simpler structures and lower masses may closely resemble the first galaxies to form after the Big Bang. Another fascinating aspect of the cosmic baryon cycle is its interplay with the large-scale structure of the universe. Galaxies are not isolated entities. They exist within a vast cosmic web of filaments and voids composed of dark matter and baryonic gas. The cycle is influenced by this structure, as gas flows along filaments into galaxies and is later redistributed through outflows. This interconnectedness means that the cosmic baryon cycle is not just a local phenomenon, but a critical component of the universe's overall architecture. The role of dark matter in shaping the cosmic baryon cycle cannot be overstated. Dark matter provides the gravitational framework that enables baryonic matter to accumulate and form galaxies in the first place. However, the interaction between dark matter and baryons is far from straightforward. The gravitational potential wells created by dark matter halos influence the efficiency of the cycle, determining how much gas can be retained or ejected from galaxies. In turn, the baryonic processes of star formation and feedback can modify the distribution of dark matter, creating a dynamic feedback loop that shapes both components. The study of the cosmic baryon cycle also extends to galaxy clusters, the largest gravitationally bound structures in the universe. In these environments, the cycle operates on an immense scale, with hot gas filling the intracluster medium and interacting with the galaxies within the cluster. The presence of this gas provides a unique opportunity to study the cycle in action, as it can be observed in multiple wavelengths, from X-rays emitted by the hot gas to radio waves tracing outflows from AGN. These observations help to unravel the complex interplay between the different components of the cycle in these extreme environments. The cosmic baryon cycle's impact on the intergalactic medium, IGM, is another area of active research. The IGM serves as both a reservoir and a conduit for baryonic matter, playing a critical role in the cycle's operation. Understanding the properties of the IGM, such as its temperature, density, and chemical composition, provides essential context for studying the cycle. Observations of the IGM are challenging due to its diffuse nature, but advances in instrumentation and techniques are gradually revealing its secrets. A key challenge in studying the cosmic baryon cycle is the vast range of scales it encompasses, from the microscopic processes governing gas cooling and star formation to the macroscopic dynamics of galaxies and cosmic structures. Bridging these scales requires a multidisciplinary approach, combining insights from astrophysics, cosmology, and computational science. The development of sophisticated simulations has been particularly transformative, allowing scientists to model the cycle in unprecedented detail and test hypotheses against observational data. Despite the significant progress made in recent years, many questions about the cosmic baryon cycle remain unanswered. For instance, the precise mechanisms driving galactic outflows are still poorly understood, particularly the role of magnetic fields, cosmic rays, and turbulence. Similarly, the processes governing the accretion of gas onto galaxies are complex and influenced by a multitude of factors, from the surrounding environment to the internal dynamics of the galaxy. Understanding the cosmic baryon cycle also has implications for the search for life in the universe. The cycle determines the availability of elements like carbon, oxygen, and nitrogen, which are essential for life as we know it. By shaping the chemical composition of galaxies and their environments, the cycle influences the conditions under which planets and potentially habitable environments can form. In this sense, the cosmic baryon cycle is not just a cosmic process, but a potential determinant of the prevalence of life in the universe. As we continue to study the cosmic baryon cycle, we are reminded of the profound interconnectedness of the cosmos. Every observation, every simulation, and every theory brings us closer to understanding the grand narrative of the universe. The cycle is a testament to the beauty and complexity of nature, where even the simplest particles participate in an intricate dance of creation and destruction. By unraveling the mysteries of the cosmic baryon cycle, we are not just uncovering the mechanics of the universe, we are uncovering its soul. The cosmic baryon cycle study also brings attention to the role of timing and cosmic epochs. The universe has undergone distinct phases of evolution, each characterized by varying rates and scales of baryon cycling. In the early universe, the cosmic baryon cycle was dominated by rapid cooling and the formation of the first stars and galaxies. This era, known as the epoch of reionization, saw an intense interplay between the first luminous objects and the surrounding intergalactic medium. The ultraviolet light from these stars reionized the neutral hydrogen in the universe, fundamentally altering the nature of the IGM and the cycle itself. During this time, the inflows of pristine gas were particularly critical. This gas, primarily hydrogen and helium formed in the Big Bang, provided the raw material for the first generation of stars. These stars, in turn, began to synthesize heavier elements through nuclear fusion, enriching the surrounding medium when they ended their lives in spectacular supernovae. This enrichment seeded the next wave of star formation, kickstarting the feedback loops that would come to define the cosmic baryon cycle in later epochs. As the universe aged, the growth of galaxies and the formation of large-scale structures introduced additional complexities to the cycle. Galaxy mergers became more common, driving intense bursts of star formation and fueling active galactic nuclei, AGN. These events had a profound impact on the baryon cycle, generating powerful outflows capable of expelling significant amounts of gas into the intergalactic medium. At the same time, the accretion of gas along cosmic filaments ensured a steady supply of fresh material, maintaining the cycle's momentum. In the modern universe, the cosmic baryon cycle continues to operate, albeit at a slower pace. Many galaxies, including our own Milky Way, have settled into a quasi-equilibrium state where inflows and outflows are relatively balanced. However, the cycle is still dynamic, with ongoing star formation, supernova explosions, and AGN activity driving the redistribution of baryonic matter. Observations of nearby galaxies provide invaluable insights into this stage of the cycle, allowing astronomers to study its processes in unprecedented detail. The role of metallicity, an astrophysical term referring to the abundance of elements heavier than helium, is a particularly intriguing aspect of the cosmic baryon cycle. Metallicity serves as a cosmic fingerprint, revealing the history of star formation and feedback in a given region of the universe. By studying the metallicity of stars, gas, and the intergalactic medium, scientists can trace the flow of baryonic matter through the cycle and reconstruct the evolutionary pathways of galaxies. This research has revealed striking variations in metallicity across different environments, highlighting the diverse outcomes of the cycle's processes. One of the most challenging aspects of studying the cosmic baryon cycle is the need for comprehensive, multi-wavelength observations. The cycle involves a wide range of physical processes, each emitting light at different wavelengths. For example, the cooling of hot gas is best observed in X-rays, while star formation is traced by ultraviolet and optical light. Meanwhile, cold gas inflows and outflows can be detected using radio and submillimeter wavelengths. Combining these observations into a cohesive picture requires not only advanced instrumentation but also sophisticated analytical techniques. Fortunately, recent technological advancements are enabling groundbreaking discoveries. Telescopes like the James Webb Space Telescope, JWST, and the Atacama Large Millimeter/Submillimeter Array, ALMA, are providing unprecedented views of the cosmic baryon cycle, from the formation of the earliest galaxies to the intricate details of gas flows in nearby systems. These observations are complemented by large-scale surveys, such as the Sloan Digital Sky Survey (SDSS) and the upcoming Vera C. Rubin Observatory, which map the distribution of galaxies and the intergalactic medium across vast cosmic scales. In addition to observational advances, the development of high-resolution simulations has revolutionized our understanding of the cosmic baryon cycle. These simulations, which model the complex interplay between baryonic matter, dark matter, and cosmic structures, allow scientists to test hypotheses and explore scenarios that are difficult or impossible to observe directly. For example, simulations have provided valuable insights into the role of turbulence in regulating gas flows and the impact of cosmic rays on outflows. They have also highlighted the importance of small-scale processes, such as the formation of molecular clouds, in shaping the cycle. The cosmic baryon cycle is not only a key driver of galactic evolution, but also a critical factor in shaping the observable universe. The distribution of baryonic matter determines the appearance of galaxies, the brightness of quasars, and even the cosmic microwave background's subtle imprints. By studying the cycle, scientists are uncovering the physical principles that govern these phenomena, bringing us closer to a unified understanding of the cosmos. As we delve deeper into the cosmic baryon cycle, we are also uncovering its broader implications for cosmology and fundamental physics. For example, the cycle's efficiency in converting gas into stars has direct implications for the universe's overall star formation rate, which in turn affects the production of light and heavy elements. These processes are critical for understanding the cosmic energy budget and the conditions under which galaxies and structures form. The study of the cosmic baryon cycle is also shedding light on the mysterious dark energy that drives the universe's accelerated expansion. By examining the distribution and behavior of baryonic matter across cosmic scales, scientists can test models of dark energy and explore its interaction with matter. This research has the potential to uncover new physics, offering insights into one of the most profound mysteries of our time. Ultimately, the cosmic baryon cycle is a story of transformation, interconnectedness, and cosmic creativity. It is a process that transcends the boundaries of individual galaxies, weaving a web of relationships that spans the universe. By studying this cycle, we are not only unraveling the mechanics of the cosmos but also gaining a deeper appreciation for the unity and complexity of the natural world. The cosmic baryon cycle also provides an essential framework for understanding how the universe became structured in its current form. On a fundamental level, the baryon cycling process helps regulate the star formation efficiency in galaxies, dictating how bright and massive these systems become over time. This regulation process is finely tuned. Too much gas retained within galaxies can result in runaway star formation, while too little gas available due to excessive outflows can leave galaxies stagnant and unable to grow. The interplay between inflows and outflows ensures a delicate balance, one that governs the diversity of galaxy types observed across the universe. One fascinating aspect of this cycle is its dependence on the cosmic web, the large-scale structure of the universe formed by the gravitational interaction of dark matter and baryonic matter. The cosmic web comprises dense nodes of galaxy clusters connected by filaments of gas and galaxies, with vast, empty voids in between. The filaments of the cosmic web act as highways for baryons, channeling gas from the intergalactic medium into galaxies. These filaments play a vital role in the recycling of matter, feeding galaxies with fresh material while also redistributing enriched gas ejected by galactic winds. In particular, the feeding mechanisms of galaxies within the cosmic web reveal much about the dynamics of the baryon cycle. Galaxies located in dense regions of the web, such as clusters, often experience a different evolutionary path compared to those in isolated regions. Within clusters, the hot gas in the intracluster medium can strip away a galaxy's outer layers of gas through a process known as ram pressure stripping. This deprives galaxies of the cold gas needed for star formation, effectively halting their growth. However, the ejected gas does not vanish. it becomes part of the intracluster medium and may eventually cool and condense, contributing to future baryonic cycling on larger scales. In contrast, galaxies in less dense environments are more likely to experience uninterrupted inflows of cold gas from the filaments, maintaining their ability to form stars. This environmental dependence of the baryon cycle highlights the interconnected nature of galaxies and the larger structures to which they belong. It also underscores the significance of environment in determining a galaxy's evolutionary trajectory, shaping the cosmic tapestry over billions of years. The cosmic baryon cycle is also deeply influenced by the properties of the intergalactic medium, particularly its temperature, density, and chemical composition. In the early universe, the IgM was a nearly uniform sea of hydrogen and helium, but as galaxies formed and evolved, they began to pollute the IgM with heavier elements through supernova explosions and galactic winds. This enrichment process has left a measurable imprint on the IgM, with modern observations revealing the widespread presence of metals in regions far from galaxies. The distribution of these metals provides a window into the history of baryonic cycling, allowing scientists to track the flow of matter across cosmic time. Another crucial factor in the cosmic baryon cycle is the role of active galactic nuclei (AGN), the luminous centers of galaxies powered by supermassive black holes. AGN are among the most energetic phenomena in the universe, capable of releasing vast amounts of energy in the form of radiation, winds, and jets. This energy can have a profound impact on the surrounding gas, heating it to temperatures that prevent it from cooling and collapsing into stars. This phenomenon, known as AGN feedback, is a key regulator of the baryon cycle, particularly in massive galaxies and galaxy clusters. AGN feedback operates on multiple scales, from the immediate vicinity of the black hole to the larger scale environment of the host galaxy and beyond. On small scales, the intense radiation from the AGN can ionize and expel gas from the galactic nucleus, creating powerful outflows that carry enriched material into the intergalactic medium. On larger scales, the jets emitted by AGN can inflate bubbles of hot gas in the intracluster medium, distributing energy over millions of light-years and suppressing star formation across entire galaxy clusters. This feedback mechanism ensures that the baryon cycle remains dynamic, preventing excessive gas accumulation in galaxies and maintaining the balance between inflows and outflows. However, the exact mechanisms of AGN feedback are still not fully understood. Observations and simulations have revealed a wide range of feedback behaviors, from gentle winds that gradually remove gas to violent eruptions that expel material at high velocities. These variations suggest that AGN feedback is influenced by a complex interplay of factors, including the black hole's mass, the properties of the host galaxy, and the surrounding environment. Understanding these factors is a major focus of current research, as it holds the key to unraveling the role of AGN in the cosmic baryon cycle. The cosmic baryon cycle is also intimately linked to the cosmic timeline, with different processes dominating at different epochs. In the early universe, the cycle was driven primarily by the rapid cooling and accretion of gas, leading to the formation of the first stars and galaxies. This era, known as the epoch of reionization, marked a turning point in the universe's evolution, as the light from these early objects ionized the surrounding gas and reshaped the IgM. The feedback from these early stars and galaxies played a crucial role in regulating the baryon cycle, influencing the subsequent formation of structures. In the present-day universe, the baryon cycle operates on a more gradual timescale, with inflows and outflows reaching a state of relative equilibrium. Observations of nearby galaxies reveal a wide range of baryonic behaviors, from the steady accretion of gas in spiral galaxies to the violent outflows in starburst galaxies and AGN. These observations provide a snapshot of the baryon cycle in action, offering valuable insights into its processes and their impact on galactic evolution. The study of the cosmic baryon cycle also raises profound questions about the fate of baryonic matter in the universe. While much of the baryonic matter is locked up in stars, planets, and gas within galaxies, a significant fraction remains in the intergalactic medium, where it is difficult to detect. This missing baryon problem has been a long-standing puzzle in astrophysics, with recent studies suggesting that much of the missing matter resides in diffuse gas filaments within the cosmic web. Unraveling the distribution and behavior of this gas is a key challenge for understanding the full scope of the baryon cycle. The missing baryon problem is particularly intriguing because it underscores just how much of the universe's matter remains hidden in plain sight. While we can observe the visible stars, galaxies, and even the faintest hints of intergalactic gas through various telescopes and methods, a significant portion of baryonic matter is thought to be in a diffuse and highly ionized state, spread across vast distances between galaxies. This gas is elusive because it emits very little light, making it challenging to detect using traditional observational techniques. However, recent advances in both observational technology and theoretical models have begun to shine light on these hidden components of the baryon cycle, gradually revealing the missing baryons that have been absent from our models for decades. The process of tracking and mapping these baryons is particularly challenging due to the nature of the cosmic web. This web is vast, stretching across billions of light-years, with its threads of gas connecting different galaxy clusters and nodes. These filaments act as the highways through which matter is transferred across the universe, and they are thought to be the key to understanding the distribution of missing baryons. By using advanced techniques like the detection of weak X-ray emissions, the observation of absorption lines in the spectra of distant quasars, and simulations that model the behavior of cosmic gas, astronomers are beginning to map out the gas within the cosmic web in more detail. These observations suggest that much of the universe's missing baryons may reside in these filaments, which are too faint to be seen directly but detectable through their interactions with light from distant objects. These findings also have profound implications for the study of galactic evolution. The intergalactic gas within the cosmic web is not just a passive reservoir of matter, it plays a dynamic role in the formation and growth of galaxies. As gas is funneled into galaxies through the filaments, it becomes the raw material from which new stars are born. However, this process is not without its complications. For instance, galaxies with more massive black holes or more active AGN may push gas out of their systems through feedback mechanisms, limiting their ability to continue growing. On the other hand, smaller galaxies may be able to maintain steady inflows, allowing them to gradually accumulate matter and form stars over longer periods. In this way, the cosmic web is not only a conduit for matter but also a battleground where the forces of feedback, gravity, and star formation are at play. Another aspect of the baryon cycle that has emerged in recent years is its influence on the large-scale structure of the universe. The distribution of matter in the cosmos is not random but rather follows a pattern that has been shaped by the interaction of dark matter, dark energy, and baryonic matter. This structure is composed of galaxies, galaxy clusters, and the vast voids between them, all interconnected by the filaments of the cosmic web. These filaments, which act as channels for the movement of gas and stars, also serve as a way to trace the history of baryonic matter in the universe. The matter in these filaments was not created in a uniform way. Instead, it has been shaped by the complex interplay of gravity, dark matter, and the evolution of the cosmic web itself. Understanding how matter moves and evolves within this web can offer insights into the universe's past and future, including the formation of the first galaxies, the development of large-scale cosmic structures, and even the fate of the universe itself. The role of the cosmic baryon cycle extends far beyond the present-day universe. Looking at the distant past, it is clear that the processes we see unfolding today were not always in place. During the early stages of the universe, shortly after the Big Bang, baryonic matter existed primarily as a hot, dense plasma. Over time, as the universe expanded and cooled, this plasma began to condense and form the first atoms, primarily hydrogen and helium. The subsequent formation of the first stars and galaxies marked a dramatic shift in the baryon cycle, as these objects began to process the raw gas and convert it into heavier elements. The recycling of this matter between stars, galaxies, and the intergalactic medium began, setting the stage for the evolution of cosmic structures. During the epoch of reionization, which occurred roughly 13 billion years ago, the first galaxies and stars began to form and light up the universe. The radiation from these early stars ionized the surrounding hydrogen, marking a crucial phase in the baryons cycle. This era of reionization was not just a time of dramatic cosmic change but also a critical period of feedback between the galaxies and the intergalactic medium. As these early galaxies expelled material into space through supernova explosions and galactic winds, they helped shape the composition of the intergalactic gas. This enriched the surrounding medium with heavier elements, such as carbon, oxygen, and iron, setting the stage for the complex chemical processes that we observe today. As the universe continued to evolve, the cycle of recycling baryonic matter became more intricate. Star formation continued at a vigorous pace, and galaxies began to merge and interact with one another. These galactic collisions triggered new rounds of star formation, but they also caused powerful bursts of energy that could expel vast amounts of gas from galaxies, enriching the surrounding cosmic medium with the remnants of stellar explosions. These interactions between galaxies, stars, and gas formed the foundation for the intricate and ever-changing baryon cycle that we observe in the universe today. At the heart of these cycles is the interplay between gas, stars, and black holes. The formation of stars is deeply tied to the cooling and condensing of gas, which gradually forms dense clouds that collapse to form new stars. However, this process is not always straightforward. Supernova explosions, the death throes of massive stars, can create shock waves that heat the surrounding gas, preventing it from condensing into new stars. On larger scales, the growth of supermassive black holes in the centers of galaxies can further disrupt the star formation process. These black holes can expel energy and matter in the form of powerful jets and winds, suppressing star formation and pushing gas out into the larger intergalactic medium. Despite these disruptions, the overall trend in the universe is one of continuous recycling. The gas that is expelled from galaxies or heated by black holes doesn't simply disappear. Instead, it contributes to the cosmic baryon cycle by enriching the intergalactic medium and feeding other galaxies or clusters. Even the gas that escapes entirely from galaxies into the vast voids of space eventually contributes to the formation of new structures, as it is reaccumulated by the gravity of other galaxies or the cosmic web itself. Ultimately, the cosmic baryon cycle is a never-ending, dynamic process that shapes the evolution of the universe in ways that we are just beginning to understand. By tracing the flow of baryonic matter through the cosmos, scientists are able to unlock the mysteries of galaxy formation, star creation, and the large-scale structure of the universe. And in doing so, they are revealing the intricate, interconnected web of matter that defines the very fabric of the cosmos. The cosmic baryon cycle is also intrinsically tied to the process of galaxy formation. Galaxies are not static objects. They are constantly evolving and growing through complex interactions with the intergalactic medium. As matter cycles between galaxies, stars, and the intergalactic gas, it profoundly impacts the way galaxies form, mature, and die. The ongoing exchange of matter is essential for understanding how galaxies obtain the raw materials needed to create new stars, and ultimately, how galaxies evolve over time. At the heart of galaxy formation is the process of gas cooling and collapsing. In the early universe, after the Big Bang, the matter in the cosmos was mostly hydrogen and helium gas. This gas, spread throughout the vastness of space, began to cool as the universe expanded. Under the influence of gravity, regions of higher density began to collapse, creating clumps of gas that eventually formed the first stars and galaxies. This early stage in the cycle is critical because it marks the beginning of the recycling of matter that will continue for billions of years. These first-generation stars, often referred to as population 3 stars, were massive and short-lived. When they exploded as supernovae, they not only enriched the surrounding gas with heavier elements, but also triggered the formation of new stars and galaxies. This process is a key example of how the baryon cycle operates on large scales. The matter from one generation of stars contributes to the creation of the next generation. As stars continue to form, die, and release their materials, the process of recycling matter in the universe continues in an endless loop. Over time, galaxies became more complex, and the recycling of matter within them became more efficient. The interstellar medium, ISM, within galaxies is made up of gas and dust that is constantly cycling through various stages. This gas is primarily composed of hydrogen, which can be found in a variety of forms, including atomic hydrogen, molecular hydrogen, and ionized hydrogen. When stars form, they pull gas from the ISM, and after stars die, they release gas back into the ISM, often in the form of supernova explosions or stellar winds. This material, enriched with the products of stellar nucleosynthesis, mixes with the surrounding gas, contributing to the next cycle of star formation. But not all of the gas remains within galaxies. Some of it is expelled into the intergalactic medium, especially in regions of intense star formation or active galactic nuclei (AGN). These regions are characterized by the presence of supermassive black holes at the centers of galaxies, which can drive powerful outflows of gas and energy. These outflows, often referred to as galactic winds, carry matter out of galaxies, contributing to the wider baryons cycle. While this expelled gas may be lost from the galaxy itself, it doesn't disappear. It enriches the surrounding intergalactic medium, and can eventually be recycled back into other galaxies or filaments within the cosmic web. The expulsion of gas through galactic winds is not a one-way process. Gas from the intergalactic medium can also be drawn into galaxies, particularly in regions where the gravitational pull of a galaxy or a cluster of galaxies is strong. This process, known as accretion, occurs when gas from the cosmic web is funneled into galaxies, feeding new rounds of star formation and adding to the complexity of the baryon cycle. The interplay between accretion and feedback is crucial for determining the growth and evolution of galaxies over cosmic time. As galaxies interact and collide, their gas and stars are also involved in a complex exchange. Galaxy mergers, which occur when two galaxies pass close enough to each other to be gravitationally attracted, can lead to the formation of new stars, the redistribution of gas, and the triggering of supernovae. These interactions help drive the baryons cycle by redistributing matter within galaxies and across larger cosmic structures. The debris from these collisions, including gas, dust, and stellar remnants, contributes to the growth of the intergalactic medium and the ongoing recycling of matter. The feedback from supermassive black holes, SMBHs, at the centers of galaxies adds another layer of complexity to the cycle. When these black holes grow by accreting matter, they can release enormous amounts of energy in the form of jets and radiation. This energy can heat and expel gas from the surrounding galaxy, limiting the amount of new star formation that occurs. These feedback processes play a critical role in regulating the amount of gas available for future star formation, effectively controlling the pace at which matter is recycled within galaxies. However, this feedback isn't always one-directional. While the energy from SMBHs can expel gas from galaxies, it can also enrich the surrounding medium, contributing to the broader cosmic baryon cycle. The energy released in these processes can ionize gas, heating it to high temperatures and causing it to expand. This heated gas can then interact with the cosmic web, contributing to the structure and evolution of the universe on much larger scales. One of the most fascinating aspects of the cosmic baryon cycle is its ability to affect the large-scale structure of the universe. The distribution of galaxies, galaxy clusters, and the vast voids between them is shaped by the movement of gas and matter. As matter cycles between galaxies, stars, and the intergalactic medium, it influences the formation of the cosmic web, the large-scale structure that connects galaxy clusters across vast distances. These connections, made up of filaments of gas and dark matter, form the scaffolding upon which galaxies and clusters are built. The filaments of the cosmic web are a key feature of the baryon cycle. These filaments are the highways through which matter is transported across the universe. As gas moves along these filaments, it can be drawn into galaxies, contributing to the process of star formation. This constant cycling of matter between galaxies and the intergalactic medium helps shape the evolution of galaxies and their environments. In many ways, the cosmic baryon cycle acts as the lifeblood of the universe, constantly recycling matter and energy, feeding galaxies, stars, and black holes, and contributing to the ongoing evolution of the cosmos. As we continue to explore the universe, both through advanced telescopes and through theoretical models, we are beginning to uncover more and more about the intricate processes that govern the movement of matter across vast distances. The mystery of the cosmic baryon cycle is far from solved, but each new discovery adds to our understanding of the universe's deep, interconnected nature. Moreover, our expanding knowledge of the baryon cycle opens the door to new insights about the future of the universe. The way in which galaxies continue to cycle matter will play a crucial role in determining the fate of the cosmos. Will galaxies eventually run out of gas, and with it, star-forming potential? Will the intergalactic medium become too diffuse to support new star formation? Or will new cycles of gas and matter continue to fuel the growth of galaxies for billions of years to come? These questions remain unanswered, but they speak to the central role that the baryon cycle plays in shaping the universe, both now and in the distant future. Ultimately, the cosmic baryon cycle serves as a reminder of the interconnectedness of all things in the universe. From the smallest atoms to the largest galaxy clusters, matter is constantly cycling and recycling, transforming from one form to another, contributing to the growth of stars, galaxies, and the very structure of the cosmos. The next time we look up at the night sky, we might see the stars shining bright above us, but beneath the surface of this vast cosmic landscape, the cycle of matter is constantly unfolding, a never-ending dance that has shaped the universe for billions of years, and will continue to do so for eons to come. As we continue to explore the vast universe, the full complexity of the cosmic baryon cycle becomes even more apparent. Understanding this cycle not only gives us insight into how matter moves through the cosmos, but also how it shapes the very fabric of the universe itself. The interactions between galaxies, stars, gas, and black holes continue to puzzle scientists, and each discovery reveals new layers to this grand cosmic mechanism. One of the most intriguing elements of the cosmic baryon cycle is its relationship to the formation of elements. The process of star formation is directly tied to the recycling of matter in the universe, and it is through this cycle that the elements necessary for life, as we know it, are created. While hydrogen and helium were formed during the Big Bang, all heavier elements, carbon, oxygen, nitrogen, and the metals we depend on, are synthesized in the cores of stars. This process, known as stellar nucleosynthesis, produces the building blocks of life. When stars die, they release these elements into the interstellar medium, enriching the gas clouds from which new stars will form. As the gas is pulled together and compressed by gravity, new stars are born, and the cycle continues. This recycling of matter is essential for the ongoing creation of elements. Without this process, the universe would be left with only hydrogen and helium, with no way to create the complex elements needed for the formation of planets and life. In this sense, the cosmic baryon cycle is responsible for the very chemistry that makes the universe as diverse and complex as we know it. This cycling of elements also has significant implications for the habitability of other planets. In regions of space where star formation is active, the interstellar medium is rich in the elements needed for life. Over time, as stars die and expel their materials into space, these elements are incorporated into new star systems, some of which may host planets capable of supporting life. The formation of habitable planets is therefore directly linked to the baryon cycle, which provides the raw materials necessary for life to emerge. In addition to star formation and element creation, the cosmic baryon cycle plays a crucial role in the regulation of the universe's overall energy budget. The continuous flow of energy between galaxies, stars, and the intergalactic medium is what drives the evolution of cosmic structures. Stars emit energy in the form of light and heat, while black holes release enormous amounts of energy in the form of radiation and jets. This energy regulates the temperature and density of the gas in the intergalactic medium, influencing the rate at which new stars can form. The feedback mechanisms between star formation, supernova explosions, and active galactic nuclei help to maintain a balance in the energy distribution across the universe. One of the more challenging aspects of studying the cosmic baryon cycle is that it operates on scales that are difficult to observe directly. The vast distances between galaxies and the immense timeframes involved in these processes make it hard to study in real time. However, astronomers have been able to piece together a picture of this cycle by studying the light emitted by distant galaxies and the properties of the intergalactic medium. Spectroscopic observations of galaxies and their surrounding gas provide clues about the amount of gas being accreted into galaxies, the rate of star formation, and the impact of feedback from supernovae and black holes. Moreover, the discovery of the cosmic microwave background radiation, CMB, has provided us with a snapshot of the universe's early conditions, allowing scientists to understand the distribution of matter and energy shortly after the Big Bang. The CMB offers critical clues about how matter was distributed in the early universe and how it evolved over billions of years, leading to the structure we observe today. By studying these cosmic relics, we can better understand the processes that govern the cosmic baryons cycle. Another aspect that has captivated researchers is the role that dark matter plays in the cosmic baryons cycle. While dark matter does not directly interact with regular matter in the way that baryons do, its gravitational influence is crucial for the formation of large-scale structures like galaxies and galaxy clusters. Dark matter helps to anchor galaxies and provide the gravitational foundation for the cosmic web. Without dark matter, galaxies would not be able to form or maintain their structure over time. In this sense, while dark matter may not directly participate in the cycling of baryons, it plays an essential role in shaping the environments where the baryons cycle can unfold. The distribution of matter, both visible and dark, across the universe is key to understanding the overall dynamics of the cosmic baryons cycle. Observations of galaxy clusters, superclusters, and voids have revealed the intricate ways in which galaxies and gas are connected across vast cosmic distances. These large-scale structures serve as a cosmic map, showing us how matter is distributed and how it flows between galaxies and the intergalactic medium. The interactions between galaxies in these large structures are essential for the recycling of matter, as gas is exchanged, accreted, and expelled in an ongoing cycle. One of the key questions in modern cosmology is how the universe will continue to evolve over time. The cosmic baryons cycle will play a central role in this evolution. As galaxies continue to form and consume gas, they will eventually exhaust their fuel, and star formation will slow down. This process, known as cosmic quenching, will lead to the cessation of star formation in many galaxies. The gas in these galaxies will be used up or expelled into the intergalactic medium, and the galaxies will become dormant. However, the recycled matter from these galaxies will continue to play a role in the broader cycle, enriching the intergalactic medium and potentially fueling the formation of new galaxies. Some scientists speculate that the eventual end of star formation will lead to a dark age in the universe, where no new stars are born and galaxies become increasingly devoid of gas. In such a scenario, the baryons cycle would slow down as galaxies become gas-deprived, and star formation ceases. However, even in this dark age, the remnants of stars and galaxies would continue to circulate matter, ensuring that the cycle does not come to a complete halt. The recycling of matter would continue, though at a reduced rate, as the universe cools and expands. The future of the cosmic baryons cycle is deeply connected to the ultimate fate of the universe itself. Whether the universe continues to expand forever, collapses in on itself, or undergoes some other dramatic transformation, the matter cycling through the cosmos will play a central role in determining its destiny. Understanding the mechanics of the baryons cycle allows us to peer into the future of the universe and to predict how it might evolve over the next several billion years. Will it continue to recycle matter and give rise to new generations of stars? Or will it slow down and enter a state of stasis? Only time and further study will tell. What is clear, however, is that the cosmic baryons cycle is an essential part of the universe's ongoing evolution. It is a process that connects the past, present, and future of the cosmos, ensuring that matter is constantly recycled, enriched, and reused. This cycle has shaped the universe from its earliest moments, and it will continue to shape it for billions of years to come. By studying this grand cosmic process, we gain not only a deeper understanding of the universe's history but also a glimpse into its future. In the grand scheme of the universe, the cosmic baryons cycle serves as a reminder of the interconnectedness of all things. From the birth and death of stars to the movement of gas across vast cosmic distances, this cycle shapes the very structure of the cosmos. It is a dynamic, ever-evolving process that drives the formation of galaxies, stars, and elements, ensuring that the universe remains in a constant state of transformation. As we continue to explore the universe, both through observation and theory, we will undoubtedly uncover even more mysteries about this fascinating cosmic cycle and its role in the evolution of everything that exists. The more we delve into the workings of the cosmic baryon cycle, the more complex and interconnected it becomes. One fascinating aspect is how the cycle is influenced by and contributes to the large-scale structure of the universe. The cosmic web, which is the vast network of galaxies, gas, and dark matter stretching across the universe, is shaped by the very processes of matter cycling. This intricate web of structures is formed by the gravitational pull of dark matter, which organizes galaxies into clusters and superclusters. The cycling of baryonic matter through stars and galaxies plays a key role in shaping this large-scale structure and how it evolves over cosmic time. Within these structures, we observe that galaxies are not isolated entities but are often connected by vast streams of gas, known as the intergalactic medium. This medium is composed of hot, diffuse gas that fills the space between galaxies and can stretch across hundreds of millions of light-years. The exchange of matter between galaxies and the intergalactic medium is an integral part of the cosmic baryon cycle. As stars form and evolve within galaxies, they expel gas and elements back into the intergalactic medium, enriching the surrounding space and influencing the formation of new stars. This constant recycling of matter is what keeps the process going, ensuring that the universe remains in a dynamic state of change. One of the most intriguing aspects of the cosmic baryon cycle is the role of feedback mechanisms in regulating the process. These feedback loops involve the interplay between star formation, supernovae explosions, and the active centers of galaxies, particularly the supermassive black holes that reside at the cores of most galaxies. Supernovae, the explosive deaths of massive stars, release large amounts of energy and materials into the surrounding space, influencing the local interstellar medium. This energy can either trigger the formation of new stars or prevent it by heating the surrounding gas and pushing it away, thereby shutting down star formation. Similarly, the intense radiation and particle outflows from supermassive black holes can have a profound effect on the surrounding gas, regulating its density and, in turn, the rate of star formation. In regions where star formation is vigorous, the gas is often heated by radiation and winds from newly formed stars, leading to the creation of hot, ionized gas clouds. These regions, known as H2 regions, are the birthplaces of new stars, but they also represent a key moment in the baryon cycle. As stars age and explode, they enrich these regions with heavy elements, perpetuating the cycle of matter recycling. In contrast, in more quiescent regions, where star formation has slowed or stopped, the interstellar gas remains cooler and less dense. This balance between star formation and quenching is a critical component of the cosmic baryon cycle, helping to maintain the delicate equilibrium of matter in the universe. The cosmic baryon cycle also plays a crucial role in the process of galaxy evolution. As gas is recycled through the cycle, it accumulates in the centers of galaxies, where it can fuel the formation of new stars or be consumed by the supermassive black hole. This cycle of matter is what drives the growth and development of galaxies over time. In the early stages of galaxy formation, gas is abundant, and star formation is rapid. As galaxies evolve, the rate of star formation slows as the available gas is used up, and the galaxies begin to quench. This process is observed in many galaxies as they age, with the most massive galaxies experiencing a complete cessation of star formation. The feedback processes between stars, black holes, and gas are responsible for the varying rates of star formation across different types of galaxies. In some galaxies, star formation is still ongoing, and the interstellar medium is rich in gas. In others, star formation has stopped, and the galaxy's gas supply has been depleted or driven out by the combined effects of supernovae and active galactic nuclei. The interplay between these factors helps to explain the diversity of galaxies observed in the universe, from small, star-forming dwarf galaxies to massive, quiescent ellipticals. Each galaxy's position in the cosmic baryon cycle influences its appearance, structure, and evolution. Another fascinating element of the cosmic baryon cycle is its connection to the evolution of the universe as a whole. The cycle is closely tied to the cosmic timeline, with the early universe having a different structure and composition than the universe we see today. In the first few 100 million years after the Big Bang, the universe was filled with a hot, dense gas of hydrogen and helium. As the universe cooled and expanded, matter began to clump together, forming the first stars and galaxies. These early stars, often massive and short-lived, were the first to enrich the surrounding gas with heavier elements. Over billions of years, this process of star formation, supernovae, and feedback from black holes led to the diverse array of galaxies and cosmic structures we observe today. As the universe continues to expand, the cosmic baryon cycle will play an essential role in shaping its future. Over time, galaxies will exhaust their gas supplies, and star formation will slow. The universe may enter a phase of cosmic quenching, where most galaxies are left without the necessary fuel to form new stars. However, the recycling of matter will not cease entirely. Even in the absence of new stars, the remnants of old stars, black holes, and gas clouds will continue to circulate through the intergalactic medium, ensuring that the baryon cycle persists, albeit at a reduced rate. Some scientists speculate that this cosmic quenching will eventually lead to the death of galaxies, as they become dark and devoid of gas. This scenario, while still a subject of debate, suggests that the universe may enter a long period of stasis, with little new star formation or growth of cosmic structures. However, others propose that new mechanisms may emerge to continue the process of matter recycling, ensuring that the baryon cycle remains active even in the far future. Whether through the influence of dark energy, the discovery of new types of matter or energy, or the emergence of new cosmic events, the future of the cosmic baryon cycle remains an exciting and mysterious frontier in astrophysics. In the quest to understand the cosmic baryon cycle, researchers are continually developing new tools and methods to observe and model the processes at work. The next generation of telescopes, including those that will be capable of observing the earliest galaxies and the most distant regions of the universe, will provide invaluable insights into the baryon cycle's role in shaping the cosmos. From observing the gas clouds between galaxies to detecting the faintest signals from ancient stars, these advancements will help to unlock even more secrets of the universe's history and its future. Ultimately, the cosmic baryon cycle is not just a fascinating subject for study, it is the very engine of the universe's evolution. It is responsible for the formation of galaxies, stars, planets, and the elements that make up everything we see around us. It is the process through which matter is constantly recycled and transformed, ensuring that the universe remains a dynamic and ever-changing system. The more we understand this process, the more we can appreciate the complex, interconnected nature of the universe itself. The cosmic baryon cycle is a testament to the incredible resilience of the cosmos, a never-ending cycle that has shaped, and will continue to shape, the very fabric of space and time. The implications of the cosmic baryon cycle extend beyond simply understanding how matter is recycled in the universe. By observing this intricate process, scientists have been able to gain deeper insights into the origins of the elements we find in our own solar system. The elements heavier than hydrogen and helium, such as carbon, oxygen, nitrogen, and iron, are the building blocks of life as we know it, yet they were not present in the early universe. These elements were forged in the hearts of stars and distributed through supernovae and other explosive events, gradually enriching the interstellar and intergalactic medium. In fact, the process of stellar nucleosynthesis, the formation of new elements within stars, drives much of the matter cycling. Through the fusion of lighter elements like hydrogen and helium, stars produce the heavier elements that are necessary for planet formation, life, and even the construction of future stars. These elements are released into space when stars die in a violent end, either as a supernova explosion or as a more peaceful shedding of material in the case of lower-mass stars. Over billions of years, these elements contribute to the creation of new stars, planets, and even entire galaxies, creating a cosmic web of life that continuously renews itself. The enriched gas clouds formed from the death of stars are critical for the formation of new generations of stars. This cycle of stellar birth, death, and rebirth is not only vital for the ongoing existence of galaxies, but also for the overall evolution of the universe. Without this continuous exchange of matter between the stars, the interstellar medium, and galaxies, the universe would stagnate, and the formation of new stars and galaxies would cease. As galaxies evolve, they also play a significant role in how matter circulates through the universe. Galaxies are not simply isolated entities. They are interconnected by the flows of gas, dark matter, and gravitational forces. The larger a galaxy becomes, the more it can interact with the surrounding environment. The gas within a galaxy can be swept up into the intergalactic medium, where it can be reaccumulated by other galaxies, continuing the process of recycling. Conversely, galaxies can also attract gas from their surroundings, a process known as galactic accretion, which can replenish the gas reservoirs of galaxies that have already formed stars and are no longer able to create new ones on their own. In some cases, the interaction between galaxies can result in their merger, a phenomenon that is an essential part of galaxy evolution. These galactic mergers bring vast amounts of gas together, triggering bursts of star formation in what is known as a starburst. The merging process can significantly alter the structure and future of a galaxy, depending on the type and scale of the interaction. These mergers can lead to the formation of new supermassive black holes and even more extensive recycling of baryonic matter across the merging galaxies. The role of dark matter in this cycle also cannot be overstated. Although dark matter is not directly involved in the cycling of baryonic matter, it is the invisible scaffolding that helps to hold the universe together. Dark matter makes up approximately 85% of the matter in the universe, yet it does not interact with light, making it nearly impossible to detect directly. However, its gravitational pull affects the motion of galaxies and the behavior of the cosmic web. Without dark matter's influence, galaxies would not form in the same way, and the matter cycling through the baryons cycle would behave very differently. Understanding how dark matter interacts with regular matter is one of the biggest challenges in modern astrophysics, but it is a key element in understanding the full picture of cosmic evolution. Another fascinating aspect of the cosmic baryon cycle is the role of the black hole at the center of most galaxies. Supermassive black holes are thought to be present in nearly every galaxy, and their gravitational pull can have profound effects on the surrounding gas. In fact, these black holes can influence star formation in their host galaxies by regulating the flow of gas into and out of the galaxy. When the black hole is actively consuming material, it releases enormous amounts of energy in the form of radiation and jets of particles, which can either encourage or suppress star formation in the galaxy. This is an example of feedback mechanisms at play, as the black hole interacts with its environment to shape the future of the galaxy. Interestingly, supermassive black holes and the cosmic baryon cycle are also connected through the process of feedback. The matter that falls into a black hole is not lost forever. It is heated to extreme temperatures as it spirals inward, and this process releases large amounts of energy. Some of this energy is radiated outward in powerful jets, while the rest can be deposited back into the surrounding gas. This feedback can regulate the amount of gas available for star formation, and it is believed to be a key factor in preventing galaxies from becoming overstuffed with stars. In some galaxies, the feedback from the central black hole has been so strong that it has shut down star formation altogether, turning the galaxy into a red and dead system where no new stars are born. As we consider the future of the cosmic baryon cycle, it's important to think about how the recycling of matter may evolve over time. The universe is currently expanding, with galaxies moving away from each other as the fabric of space itself stretches. As galaxies move farther apart, the amount of matter available for recycling may decrease. Gas that was once shared between galaxies may become more isolated, and the rate of star formation could slow down as a result. Eventually, galaxies may reach a point where they no longer have enough gas to form new stars, leading to what scientists call the red and dead phase. In this phase, galaxies will continue to contain stars, but no new stars will be born. However, even in the face of this cosmic evolution, the cycle of matter recycling is likely to continue in one form or another. The remnants of dead stars, white dwarfs, neutron stars, and black holes will continue to interact with their surroundings. In the far future, it's even possible that new processes or phenomena could emerge, allowing this cycle to continue, albeit in a different form. One such possibility is the idea that the remnants of black holes could merge, creating new forms of energy and possibly even leading to the formation of new galaxies. Though this is purely speculative at this point, it opens up intriguing possibilities about the long-term future of the universe. As we venture further into the study of cosmic processes, the cosmic baryons cycle remains one of the most captivating phenomena in the universe. Understanding how matter is cycled between stars, galaxies, and the intergalactic medium is crucial for piecing together the story of the cosmos itself. It is the thread that links the birth and death of stars, the formation of galaxies, and the evolution of the universe as a whole. The insights gained from studying this cycle will not only help us better understand the past but may also offer clues about the future of the universe, and the role that recycling plays in the ongoing cosmic drama. The more we learn about the cosmic baryon cycle, the more we realize how intertwined the fates of galaxies, stars, and gas clouds truly are. They are all part of a grand cosmic recycling system that spans the entire universe, ensuring that matter is never wasted and that the universe remains a dynamic, ever-evolving place. The cycle is a testament to the resilience and adaptability of the cosmos, constantly renewing itself, creating new stars, new galaxies, and ultimately, new possibilities for the future. The complexity of the cosmic baryon cycle is not just a fascinating subject of academic research, but it also carries profound implications for our understanding of the universe's future. The recycling of matter is a process that has been occurring for billions of years, and it continues to shape the cosmos, contributing to the formation of stars, the growth of galaxies, and the enrichment of the interstellar medium. But as the universe ages, the cycle faces new challenges, and understanding how matter moves through different cosmic systems can help predict what lies ahead. One of the most intriguing questions in cosmology is how the universe will end, and the cosmic baryon cycle plays a pivotal role in this ultimate fate. As mentioned earlier, galaxies are gradually running out of gas for star formation, and this could lead to what is often referred to as the degeneration of galaxies. Once galaxies exhaust their gas supply, they will no longer be able to form new stars, and the stars they have will eventually burn out, leaving behind only remnants such as white dwarfs, neutron stars, and black holes. These stars will continue to cool and fade over vast amounts of time, but the cosmic cycle will not stop entirely. In fact, the most massive remnants of stars, black holes, may continue to play a key role in the future of the universe. Through a process known as Hawking radiation, black holes may slowly lose mass and eventually evaporate, a phenomenon that has intrigued physicists for decades. As they evaporate, they will release energy and potentially create new forms of matter. While this process takes place over incredibly long timescales, it suggests that even in the far future, the cycle of matter might continue in some form, though it will look vastly different from the dynamic systems we observe today. The transition from an active, star-forming universe to one where galaxies are largely devoid of new stars is part of a larger trend in cosmic evolution. The expansion of the universe is accelerating, driven by a mysterious force known as dark energy. As the universe continues to expand, the distances between galaxies will increase, and the interactions that drive the recycling of matter, such as galactic mergers and gas exchange between galaxies, will become less frequent. This could slow down the rate of matter cycling, but it won't stop it entirely. Moreover, there is the intriguing possibility that the matter cycling process could evolve in response to these changes. Some researchers speculate that in the far future, the universe could enter a phase dominated by the creation of smaller, more isolated stars, or perhaps the recycling process will shift entirely to other forms of matter or energy. The ultimate fate of the baryon cycle will depend on numerous factors, including the behavior of dark matter, dark energy, and the fundamental forces that govern the universe. As it stands, the cosmic baryon cycle remains one of the most fundamental and fascinating processes in cosmology. It shows us that nothing in the universe is static. Even the most inert-sounding substances, like interstellar gas, are constantly being shaped and reshaped by the forces of nature. Matter, whether it's in the form of a star, a galaxy, or an invisible gas cloud, is continuously recycled, ensuring that the universe remains dynamic and full of potential. Even as stars die and galaxies age, new opportunities for formation and renewal emerge, giving us a glimpse into the long-term resilience of the cosmos. One aspect of the cosmic baryon cycle that remains particularly elusive is the precise role of the intergalactic medium. While we know that this vast region of space, which lies between galaxies, is rich with gas and dark matter, its full impact on matter recycling is still not completely understood. This region is often thought of as the empty space between galaxies, but in reality, it is far from empty. In fact, the intergalactic medium is critical to the processes of galactic evolution. The gas present in the intergalactic medium can be drawn into galaxies through gravitational forces, replenishing their gas supply and helping fuel star formation. Similarly, when galaxies interact, they can expel gas into this intergalactic space, where it may eventually be swept away by the expanding universe. The role of the intergalactic medium also extends to the ongoing flow of matter between galaxy clusters. Galaxy clusters, which are groups of galaxies bound together by gravity, are some of the largest structures in the universe. These clusters act as major conduits for the flow of gas, dark matter, and other cosmic materials. As galaxies within a cluster interact and merge, they transfer material to the surrounding intergalactic space, enriching the medium and potentially spurring the formation of new galaxies or clusters. Understanding how matter moves between galaxies and clusters, and how it interacts with the intergalactic medium, is one of the key challenges for cosmologists in understanding the long-term dynamics of the universe. In a way, the entire process of matter cycling in the universe is akin to a complex, self-regulating system. Stars are born from gas clouds, they burn for billions of years, and when they die, they return their matter to the cosmos in a spectacular display of energy and material. The gas left behind can be recycled, forming the basis for the next generation of stars. Over time, this recycling process enriches the universe, creating the elements that are crucial for life as we know it. The cosmic baryon cycle is a cosmic feedback loop, where each stage of the cycle supports the next, ensuring that the universe is always in a state of flux, always evolving. This ongoing recycling of matter has profound implications for our understanding of life itself. The elements produced by the death of stars, such as carbon, nitrogen, and oxygen, are the building blocks of life. These elements have been spread across the universe through supernovae, stellar winds, and the interaction of galaxies, allowing life to emerge on planets like Earth. The very atoms that make up our bodies were once part of stars, traveling across space and time to eventually form the molecules that enable life to thrive. The cosmic baryon cycle also challenges us to reconsider our place in the universe. We are, quite literally, made of stardust. The atoms in our bodies, the air we breathe, and the planet we call home were all forged in the hearts of stars, recycled through the cosmos, and brought together through processes we are only beginning to understand. This realization connects us to the vast universe in a way that is deeply humbling. We are not separate from the universe. We are part of its ongoing, ever-evolving cycle of matter and energy. As we continue to explore and study the cosmos, the cosmic baryon cycle will undoubtedly remain one of the most important and awe-inspiring phenomena to unravel. Understanding how matter is recycled in the universe not only deepens our knowledge of astrophysics, but also brings us closer to the profound truth that everything in the universe is connected. From the birth of stars to the formation of galaxies and the recycling of matter through space, the cosmic baryon cycle is a reminder of the incredible complexity and interconnectedness of the universe. The cosmic baryon cycle paints a picture of a universe that is not static but rather one in which matter and energy are constantly moving, evolving, and transforming. As we dive deeper into this process, it becomes clear that every element, every atom, and every form of matter in the universe is part of a dynamic, ongoing journey that spans vast timescales and distances. One of the more fascinating aspects of the cycle is how the interstellar and intergalactic mediums serve as the stage for a kind of cosmic interplay that drives the creation and destruction of stars, galaxies, and the very fabric of matter itself. The interstellar medium, ISM for instance, is composed of gas and dust scattered across the spaces between stars within a galaxy. It's here that new stars are born, drawn from the vast reservoirs of gas, mostly hydrogen, that permeate the galactic environment. However, the ISM doesn't just provide material for star formation, it is also the repository of stellar death. When stars end their lives in violent explosions, such as supernovae, they release vast amounts of energy and matter back into the ISM. This matter enriches the ISM, introducing heavier elements like carbon, oxygen, and iron that weren't present before. This enrichment is significant because these heavier elements, which are collectively known as metals, in astrophysical terms, are the building blocks for planets and, by extension, life. Every time a new generation of stars forms from the enriched gas of the ISM, the cycle continues, with each generation of stars being more chemically complex than the last. The act of dying stars seeding the ISM with these new elements is what drives the creation of the complex, habitable environments we see on planets like Earth. Over billions of years, this process of stellar evolution and recycling ensures that the elements necessary for life are continually replenished and spread throughout the universe. The process of stellar birth and death is deeply intertwined with the broader dynamics of galaxy evolution. Galaxies themselves are not just collections of stars, but massive, ever-changing systems where stars, gas, dust, and dark matter are constantly interacting. The interplay between these components is governed by gravity, which dictates the flow of matter through the galaxy. Gas clouds, pulled by gravity, collapse to form new stars, while the death of stars in supernovae sends shockwaves through the galaxy, triggering further star formation and enriching the galaxy's gas supply. But galaxies are not isolated systems. They interact with one another in profound ways, often through collisions and mergers. When galaxies collide, their gas and dust are compressed, sparking intense bursts of star formation. At the same time, material from one galaxy can be transferred to the other, enriching the intergalactic medium and influencing the future evolution of both galaxies involved. These galactic collisions, while rare on human timescales, are a fundamental part of the universe's ongoing process of recycling matter. They reshape the structure of galaxies, alter the flow of gas, and create new environments for star formation. On an even grander scale, galaxy clusters, huge collections of galaxies bound together by gravity, serve as hubs for the flow of gas and matter across vast distances. The intergalactic medium within these clusters is rich with gas that has been stripped from individual galaxies as they collide or pass through one another. This gas, known as the intracluster medium, is incredibly hot and dense, providing the raw material for future generations of stars. The movement of matter within galaxy clusters is a vital part of the cosmic baryon cycle, as it helps ensure that the resources necessary for star formation are spread across vast regions of the universe. Even as galaxies age and run out of their initial gas supplies, they continue to interact with their surroundings, and new gas can be funneled in from the intergalactic medium or from merging galaxies. This replenishing of fuel for star formation is a key factor in preventing galaxies from entering a state of dormancy too soon. In fact, even in the present day, galaxies can continue to form stars for billions of years as they interact with their neighbors and draw gas from the broader cosmic system. While it's true that some galaxies have exhausted their star-forming potential and have become red and dead, the recycling of matter from other galaxies or through mergers can rejuvenate a galaxy and keep the cycle going. The intergalactic medium is a vast and complex environment that we are still working to understand fully. Much of the gas in this space is not visible to our current observational instruments, making it difficult to track how matter flows between galaxies and clusters. However, advances in observational techniques, such as the use of X-ray telescopes and more sensitive radio observations, are allowing astronomers to peer deeper into this enigmatic space. As our understanding of the intergalactic medium improves, we will gain a clearer picture of how it contributes to the recycling of matter across the universe and influences the larger dynamics of cosmic evolution. As we look toward the distant future, the cosmic baryon cycle will continue to play a pivotal role in the fate of the universe. The ongoing recycling of matter ensures that the universe will never truly be stagnant, even though the stars we see today will eventually fade. The death of stars, the enrichment of the interstellar medium, and the interactions between galaxies will continue to shape the structure of the universe for billions of years to come. However, this cycle may slow down as the universe continues to expand. Dark energy, the mysterious force that is accelerating the expansion of the universe, is likely to cause galaxies to move further apart over time. As the distances between galaxies increase, the frequency of galactic mergers and interactions will diminish, which could slow the recycling of matter on a cosmic scale. This may result in a more isolated universe, where matter is spread thin and the creation of new stars becomes increasingly rare. Eventually, the universe could enter what is known as the degeneration phase, a time when galaxies have exhausted their gas supplies, and the stars that remain are old and cooling. In this distant future, the cosmic baryon cycle may come to an end in the conventional sense, with galaxies becoming dark, cold remnants of their former selves. But even in this scenario, the cycle might not be over. Black holes, which are the end state for the most massive stars, could continue to play a role in the evolution of the universe, as they may slowly evaporate over incredibly long timescales, potentially creating new forms of matter in the process. The universe's final stages, as we currently understand them, could be vastly different from the vibrant, star-filled cosmos we observe today. Yet, even in its death throes, the recycling of matter could continue, in one form or another, reminding us that even the universe's most inactive periods are filled with the potential for change and transformation. The cosmic baryon cycle is a testament to the incredible resilience and adaptability of the cosmos, a never-ending dance of matter and energy that shapes the universe in ways we are only beginning to comprehend. And as we continue to study the universe, new mysteries will emerge, and our understanding of how matter is recycled will evolve. The story of the cosmic baryon cycle is far from finished, and it will continue to captivate scientists and astronomers for generations to come. For now, we can marvel at the intricate dance of matter that has shaped our universe, knowing that we are part of this ongoing cycle, linked to the stars, the galaxies, and the very fabric of the cosmos. As we journey further into the heart of the cosmic baryon cycle, it's important to recognize that this process, while incredibly intricate, is still ongoing. Despite the vast timescales involved, new developments in our understanding of the universe are providing us with fresh insights into how matter is not only recycled but also how it contributes to the larger evolutionary trajectory of the cosmos. We now know that the fate of stars, galaxies, and the intergalactic medium are inextricably linked, and the material flow between them is shaping the very structure of the universe as we see it today. One of the more fascinating areas of study is the role of black holes in this cycle. Supermassive black holes, found at the centers of most large galaxies, are often seen as the cosmic engines that drive the evolution of galaxies themselves. These behemoths exert a powerful gravitational influence, and their behavior can have profound effects on their host galaxies. The relationship between a galaxy and its central black hole is crucial to understanding the overall dynamics of the cosmic baryon cycle. These black holes can siphon off enormous amounts of gas from the surrounding galactic disk, a process known as accretion. The material that spirals into a black hole is heated to extreme temperatures, emitting radiation across the electromagnetic spectrum. This radiation can then drive powerful outflows, or winds, that sweep away gas from the galaxy's central regions. These outflows can have significant consequences for star formation within galaxies. By removing gas from the galaxy, they essentially prevent new stars from forming in the regions closest to the black hole, altering the galaxy's growth. However, black hole winds can also enrich the surrounding intergalactic medium, adding to the pool of matter available for future generations of stars. These complex interactions between black holes, their host galaxies, and the broader intergalactic medium exemplify how interconnected the cosmic baryon cycle truly is. Black holes act not only as matter sinks but as cosmic engines that help distribute matter across vast distances, enriching the larger galactic ecosystem. But black holes are not the only players in this game. Supernovae, the violent deaths of massive stars, are another critical process in the recycling of matter. When these stars explode, they release an extraordinary amount of energy, expelling heavy elements and gases into the surrounding environment. These elements are then incorporated into new stars, planets, and even life itself. In fact, many of the elements essential for life on Earth, such as carbon, oxygen, and nitrogen, were forged in the cores of ancient stars and spread across the universe in the aftermath of supernovae. This process is known as stellar nucleosynthesis, and it's a fundamental part of the baryons cycle. Moreover, supernovae play a dual role in galactic evolution. Not only do they provide the raw materials for future stars and planets, but they also trigger the collapse of nearby gas clouds, initiating new cycles of star formation. In some cases, the shockwaves from a supernova can compress the gas in a neighboring molecular cloud, causing it to collapse and form new stars. This process of feedback is a key driver in the continual recycling of matter and energy within galaxies. On even larger scales, the concept of galactic winds and feedback mechanisms extends to the entire galaxy. When a galaxy experiences a period of intense star formation, the resulting supernovae and black hole activity can expel vast amounts of gas into the surrounding space. This expelled material can flow into the intergalactic medium, enriching it with metals and other elements. These winds contribute to the overall metallicity of the universe, which is a measure of the abundance of elements heavier than hydrogen and helium. The spread of these heavier elements is critical for the formation of more complex structures, including planets and even life. However, the recycling of matter does not happen in a vacuum. The broader structure of the universe, including the dark matter that pervades the cosmos, plays a crucial role in guiding the movement of baryonic matter. Dark matter, though invisible and largely undetectable by conventional means, exerts a gravitational pull on visible matter. This hidden influence is essential for the formation of galaxies, as dark matter helps to guide the gas and dust that eventually collapse to form stars. Without dark matter's gravitational influence, galaxies as we know them would never have formed, and the cosmic baryon cycle would be a very different process. The relationship between dark matter and baryonic matter is still a topic of active research. Some theorists speculate that dark matter may even be composed of particles that interact weakly with regular matter, making it a key ingredient in the larger processes that govern the universe's evolution. As our understanding of dark matter improves, it will undoubtedly shed new light on how it influences the flow and recycling of matter across the cosmos. As we turn our attention to the distant future, it's worth considering how the cosmic baryon cycle will evolve over time. The expansion of the universe is accelerating, driven by the mysterious force known as dark energy. This accelerated expansion could ultimately result in galaxies being spread further apart, making future interactions and mergers less frequent. Over billions of years, the rate of star formation will decrease as galaxies exhaust their gas supplies. The universe will gradually grow colder and darker, with fewer stars being born. In this far future, it's possible that the recycling of matter as we know it will slow down, but it may not cease entirely. Even in this cold future, the remnants of stars and galaxies may still play a role in shaping the universe. Black holes, for example, are believed to slowly evaporate over incredibly long timescales, releasing radiation and particles into the surrounding space. This process, known as Hawking radiation, could lead to the gradual dispersal of matter over trillions of years. In some speculative theories, the remnants of black holes and other compact objects could eventually merge, leading to the formation of new structures or the emergence of new phenomena. While this future may seem distant and even grim, it highlights the ongoing nature of the cosmic baryon cycle. Matter, in one form or another, will continue to be recycled, even in the absence of star formation. Whether through black hole evaporation or other unknown processes, the fundamental principles of the baryon cycle will remain at the heart of cosmic evolution, continuing to shape the universe long after stars have ceased to shine. Thus, the story of the cosmic baryon cycle is one that spans the past, present, and future of the universe. It is a testament to the intricate, interconnected nature of all matter, from the smallest atom to the largest galaxy. The recycling of matter, the ongoing interplay between stars, black holes, and galaxies, and the flow of energy across the cosmos are the forces that drive the evolution of everything we know. The cosmic baryon cycle is not just a mechanism for matter to be recycled, it is the very essence of the universe's dynamic, ever-changing nature. As we look forward to the future of cosmic exploration, one can only wonder what new discoveries will shed light on the complexities of this process. Every breakthrough in our understanding of astrophysics, every new telescope that gazes deeper into the universe, and every new theory that emerges will bring us closer to understanding the full scope of the cosmic baryon cycle. For now, we can appreciate the marvel of this eternal recycling process, knowing that it is this very cycle that has given rise to the universe we see today and will continue to shape the cosmos for eons to come. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.